All right, everyone, welcome to another episode of the TWiML AI podcast. I am, of course, your host, Sam Charrington. Today, I'm joined by Aljosa Osep, a postdoc at the Technical University of Munich and Carnegie Mellon University. Before we jump into today's conversation, please be sure to take a moment to head over to Apple Podcasts or your listening platform of choice. And if you enjoy the podcast, please leave us a 5-star rating and review. Aljosa, welcome to the show. I'm looking forward to digging into our conversation. We'll be talking about your work in robotic vision and some of the papers you'll be presenting at CVPR. Before we get there, though, I'd love to have you introduce yourself to our audience and share a bit about how you came to work in the field.
Yes, sure. So first, thank you very much for inviting me. I'm very excited to be here today and to have this opportunity to present our work that we are going to present at the CVPR next week. So I would just start with a little bit of a background about myself. So my name is Aljosa Osep, and I was raised and born in Slovenia, a quite small country in Central Europe. Yeah, as you already mentioned, at the moment I'm working as a postdoc both at Technical University. I'm working with Laura Leal-Taché, and I'm also still working at Carnegie Mellon University, where I'm working with Deva Ramanan. So you mentioned that you would like to hear something about how I have gotten into computer vision research. So just curious, would you like to hear a shorter or the longer version?
The medium version is maybe the best.
Medium version,
Is
yeah.
it something that you always aspired to do?
I would not say always. I think it kind of has gotten gradually to me, but I would say that from a very early days, I knew that I want to. I was really interested in computer science, right, and in programming. So in one way or another, I was interested in that general field. Yeah.
Okay, and what was your first exposure to vision and machine learning and AI in general?
So I would say that my first exposure to vision, ML, and AI was actually at university. I had some of the courses on computer vision, computer graphics, and machine learning already during my bachelor studies. But even before that, as I got interested in computer programming as a kid. So at the beginning, I was interested, like as a kid, of course, I was playing computer games, right? And I was just really fascinated with games and all these virtual worlds that come together with computer games, right? So first thing that I really want to understand is how, when I was still quite young, right? How this comes to be, right? What is the logic behind all this? How one makes computer game and virtual worlds, and like all these characters that appear in the game and and behave like in somewhat intelligent way, or at least that they appear that they behave in intelligent way. So this is really how I got into more general broad direction. So through interest in computer games and computer graphics. Um, but when it comes to computer vision and machine learning, I think that some of the first memories I have about this come from the time when I was doing my bachelor studies in Slovenia. So you know that the one way you can think about graphics is it's synthesis, right? You synthesize images, right? And computer vision is kind of opposite process, right? You get images and you have to understand what is in the images, or what in the world has generated those images, right? And I really remember, like back in the days, I was watching. I know this is a bit nerdy, but I really liked Star Trek, right? And
Yeah,
one of the
you're
coolest
not alone in
things,
that.
yeah, right. And one of the coolest things, besides traveling around space and like meeting alien civilization, was also this holodeck, right? I just
Right.
find it so fascinating that they have like this immersive game that just generates content, and like you can interact with characters that computer generates, and so forth. So this seemed really cool to me. But I still remember there was this one episode that I find so fascinating where they were trying to recreate something, and they have some image of, I don't know, I don't remember exactly what it was, but they have some image and they just fed this to this holodeck, and holodeck kind of create 3D reconstruction of that image, right? Then they were analyzing what was happening in this scene or something like that. But I just remember this idea, of feeding image in and getting 3D reconstruction out, right? So I thought this was really cool. Yeah.
I should mention that you're doing your postdoc with Laura Leal Taché, or you mentioned that, but I should mention that I interviewed her around this time in 2018. I'm sure it was CVPR related, given the timing. And it sounds like in some ways you're carrying on the torch, so to speak. In talking about your research interests, it's not just computer vision, it's robot vision. What kinds of problems are you trying to solve?
I would say that in broader sense, I'm really interested in 3D dynamics in understanding, right? Also similar to research interests of Flora. So you assume that you have some mobile platform such as a robot. It's equipped with some sensors, right? It can be one camera, two cameras, or several, and LiDAR. And based on whatever sensors you have, you should be able to get as complete understanding of the world as possible, right? So you should understand the 3D geometry of the world, right? Both static and dynamic, right? You should know where objects are, right? Where cars are, where pedestrians are, and so forth. In addition to that, it's also important that you know how these objects move over time, right? And the main reason why it's so important to know how objects move or how object moved in the past, which really relates to multi-object tracking. But the main reason why we want to know this is that we have to make predictions about what happens in next seconds, right? You just can imagine that if you are walking around city or if you are driving a car, what you end up doing most time is navigating into free space, right? So this means that you don't only have to understand the statics in geometry, but you also have to know where everything that moves will be in a few seconds, right? So at a higher level, this is what interests me a lot. But if I get more specific, I was really fascinated with one particular question in past years, already during my PhD, and I'm still working on this. So um, you probably know that nowadays I would say that object detection, tracking, and even forecasting models work quite well already, right? We made huge progress in recent years, right? But there is one important limitation here, and this is it works great as long as you have enough data for particular semantic classes that you're trying to recognize, right? So, for example, if you go out, record data, you will see lots of cars and pedestrians, right? You label them, use them to train models, and everything just works fantastic, right? You can recognize cars, right? But we also have this long tail distribution of semantic classes, right? And lots of semantic classes appear in this long tail, which means that most objects are observed very infrequently, or maybe even never when you're collecting data set, right? Which just means that during your model training, you don't see some particular object classes, but you still have to recognize them if you really want to navigate around the world, right? Otherwise you might otherwise it might be really dangerous, right? If you didn't recognize something because it looks like not like anything you have seen before.
What kind of approaches are you exploring to address this long tail semantic detection problem?
Mhm. Yeah, so we explored quite some approaches in the past. So the way I started looking into this back then was, so my intuition was that to track any object, we can start with something that is based on bottom-up scene understanding, right? So current standard object detection works more in a top-down fashion, right? So existing object detection models, and bottom approach is more that you get image and you try to figure out how pixels group together so that you obtain object instance, right? So which pixels group together to obtain for example, pedestrian, car, or something else that you don't know quite what it is, but based on pixel similarity, you should be able to group these pixels together and then possibly realize that object is there and then track this object, right?
And
So
that's bottom up. What is top down?
top-down approach is for example, the most well-known top-down approach is for example, faster RCNN, right? You have a bunch of windows, we call them region proposals, right? And then based on these region proposals, you try to estimate what this proposal covers, right? Is it a car, is it a person, or is part of part of a background. So you don't go from bottom up, from pixels up, but you go from top down. So you're looking at region. Yeah, exactly. So we started looking into this bottom up approaches. Um, but very soon we actually kind of started switching back to top-down data-driven methods, but instead of trying to look at region proposals and classify them as one of the object classes that were labeled in data such as is it a car, pedestrian, cyclist, you would just um, train detectors to just tell us whether this region likely contains object or not, right? So basically data-driven, we start relying on data-driven object proposals to initialize tracks, right? One queue that we were also looking into at the very beginning was depth estimates, right? So one issue with these object proposals is that they're quite noisy, right? You will end up having like bunch of object proposals. Some of them will actually detect objects that we have in our scenes, but many of them will also just might be firing on certain background region. But the next queue you can look into is depth. So if you have region proposal that is kind of supported with depth estimates, this gives you a strong cue that there actually very likely is an object and that you should start a trajectory.
Maybe kind of popping back up a level or several. When you think about robots, are you primarily or robotic vision? Are you primarily thinking about autonomous vehicle types of use cases, or do you even have a particular ideal in mind in terms of the robot itself?
Always when I talk about research, I have a wider vision in mind. So I don't only think about autonomous vehicles. I really think about any type of robots, and I even think that we should have perception system that should be applicable to for robots that want to drive on highways, that want to drive in the inner city areas, in potentially very crowded areas, right? Then we might have delivery robots that might even merge into more of pedestrian urban areas, right? Or robots that might need to navigate around warehouses, airports, and so forth, right? So I kind of think that the robots will need to be everywhere in the future, and I think that perception systems that we develop should be general. Um, but one thing I definitely have to admit is that very often when we write papers, we kind of focus on autonomous driving applications and scenarios. And one reason for that is that we just simply have most data sets that were captured for benchmarking and training algorithms for autonomous driving. I would love to have more data sets, actually, more general data sets.
Do you have a sense for some of the ways that focusing on autonomous vehicles based on data set availability, limits applicability of the work to other types of robots?
I think that there definitely is certain bias if you are only looking at autonomous vehicle data sets, right? So, for example, these data sets are obviously always recorded outside, right? Never inside. You might, for example, also over rely on the fact that you can localize yourself outside very well with GPS, for example, right? To localize your pose. This might be impossible indoors, right? Very often is. Um, then, very often, if you look at limited scenarios such as highways, for example, your diversity of objects that you will observe will actually be quite limited, right? So you learn how to recognize cars, trucks, buses, and a few other classes, and you just think you know how to handle everything, right? But this is definitely not true, right? Or visual world is way richer than that.
Speaking of localization, one of the papers that you're presenting at CVPR is called Text to Pause, Text to Point Cloud, Cross-Modal Localization. Let's dig into that a little bit. What's the kind of big picture problem that you're trying to solve with this paper?
I would actually start a bit with motivation for this. Before I even do that, let me just already tell you upfront that this paper is about localizing position within a map, 3D map of the environment based on a textual description of what is in the surrounding, right? You can imagine yourself that you are somewhere in the city. You don't know where exactly. You see some things around, right? There might be church in front of you, some trees, or something like that, and you're explaining to your friend what you see, and your friend should realize where you are based on this description, right? If your friend, of course, knows the rough environment of the city where you're in, right? And yeah, I imagine that in the future, robots will, of course, be used for many things, such as, for example, food delivery, right? Or like instead of Uber drivers picking us up to transport us somewhere, just robots will come to pick us up, right? And sometimes a GPS stack works great, but not always, right? And one thing that, for example, is particularly realized is particularly frustrating. Usually, where we are somewhere at the campus, right? Let it be Technical University of Munich or Carnegie Mellon campus, we often have meetings and we use food delivery services to deliver us food, right? And you would think that this is easy to find us, right? But it turns out it's really not. So what we end up doing, for example, if you use DoorDash, for example, you write a detailed description on how to reach us, right? And even after this detailed description, where, for example, Smith Hall is where I was working until recently, they would still very often get lost at the campus and call us and ask for more directions, right? And so it's always a bit of a hassle. So this is why we also envision that when the robots will take over, we also need to find a way to communicate with them where they need to go, right? And we want to do this communication in natural language, because natural language is what us humans are used to communicate. So this is like more like a overall vision, right? Now, if I get more to the task that this paper is addressing. So here I have to say upfront that this is one of the first investigation of this problem, right? So we had to take quite some shortcuts to making this investigation of this problem feasible, right?
Just hearing the way you describe the problem, it strikes me that there are, of course, multiple ways to come at it. One is, the paper is called Text to Point Cloud, can also envision like text to landmark, somehow trying to localize not necessarily where you are, but the landmarks that you're describing, and somehow triangulate from that. Talk a little bit more about the way you set up the problem.
Sure, sure. So you exactly. So this comment was just spot on, because this is actually the part of what the method does, right? Triangulating landmarks, right? I mean, this is the second stage. So we have like coarse localization stage and fine localization stage, right? So what you just mentioned comes into the fine phase. I will just first touch the coarse phase, and then I will get back to this, right? So in the coarse phase, we basically just split the 3D point cloud of the city or of some neighborhood into rectangular tiles, right? I don't remember what exactly the size is, but it's like a bit larger area that you first have to find, right? So first you want to find like this rectangular area in where you very likely you are located in, right?
And when you say tiles, are you thinking like OpenStreetMap tiles or something along those lines?
Now we actually have in practice LiDAR point clouds, so maps that were built from LiDAR point clouds. And the data set we actually use for that is the new Kitty 360 data set from a research group of Andreas Geiger. But this data set, of course, contains only this point clouds maps and no textual description, right? But this is how we actually generated data set. It's a different story.
I'm curious, your starting assumption is, are you assuming, no GPS, or, coarse GPS, and you're using that for the first phase, and then you're using the text base for the second phase?
So this is also a great question, and actually we assume no GPS. The only assumption we make is that we have instance segmentations available in our map, right? So that we have, we know where the houses are, we know where the trees are, and so forth. So we assume instance and semantic information in our maps.
And how fine grained are your classes? Like, do you just have building, 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 or do you have church, supermarket, campus building, whatever?
No, we don't have that fine-grained information. It's more like
Okay.
building tree, car, road,
Yeah.
and so forth. Yeah, yeah.
Okay. All right, so go on and finish with the first part of the method.
So first part is just coarse localization, but you could also use GPS for that. That's true. But since we didn't have GPS, we just pose this as a retrieval problem, right? We have textual descriptions, we have our point cloud patches, and we just learned joint embedding space for both, right? Similar to how Clip works, where they aligned images and textual descriptions, but you align point clouds and textual descriptions, and based on this learned joint embedding space, you can then, based on textual description, get like a list of most likely cells that contain your object. So this is the coarse localization step.
It strikes me that there's like a, I don't know, something that I think of as like a bootstrapping problem. Like, if I'm giving directions, I assume a certain amount of knowledge that would be hard to get from instance labels. Like I'm, on the Wash U campus, or someplace that I'm at a Starbucks or something like that. Is that kind of knowledge being introduced somewhere?
Not yet, and I think this is right now the biggest limitation of our method. So to incorporate such a fine-grained information, we would have to go a step further, and align our point clouds with something like you mentioned earlier, OpenStreetMap, right? And then you actually get access to such fine-grained information, right? So what kind of building is it, Starbucks sign, and so forth. But in this paper, we didn't have that available. I mean, it's we consider this as a future work, but we haven't.
You have to start somewhere. But it sounds like then conclusion would be that you're trying to localize within a relatively constrained area.
I'm not sure what with constraint means, because in principle this should work anywhere in the city area for which we have a map in form of point clouds, right? But of course, there is this restriction that if I just tell you that I see, I don't know, traffic sign in front, church on the right, something else here and there, right? This description fits several locations in the city, right? So you have this uncertainty, right? Of where you are, and if you wanted to make this non-ambiguous, you would really either have to go for example, GPS that coarsely localizes you, right? Then this narrows down the search space, or you would have to have information such as, is there Starbucks next to me, or street name, or something like that, right? Something that really severely narrows down the initial search stage, right?
Or even a dialogue based approach where the system can identify differentiating characteristics of the three places and ask you, do you see a street sign near you, or something like that?
Mm-hmm. Yeah, that also, I think it's very important that we incorporate into this process in the future, because of course this is how conversation with humans work, right? It's not like you just
Hmm.
describe where you are and then the other person just click knows where you are.
Right, right. Okay, so that's kind of the course part of the course phase of the method. What's the fine phase, or the second part?
When it comes to the find phase, we do pretty much exactly what you said earlier, right? So based on descriptions, find the landmarks that you refer to, right? So if you mention a sign, then the network has to realize that there was a sign mentioned in the sentence, and align this with instance of a sign within your rectangular area, right? So you kind of match um, words that refer to objects with instances, and once you do this matching, you regress offset to those.
And is success for the model returning a list of possible locations, or are you then further trying to, you know, uh, guess or predict which of the locations the user? Do you apply some kind of confidence to a list, or are you only predicting one with a confidence level? Like, what's the output of the model?
Yeah, so we predict several possible locations, and the reason for that is the coarse localization step that is inherently uncertain, right? So you might be in several cells, right? So you get a ranked list, and then the evaluation is also done with respect to top k hits. So you look like localization you look at localization retrieval success with respect to top 5, top 10, or top 15 matches.
How did you evaluate the method?
So we actually evaluated a method on data set that we generated on top of Kitty 360.
Ah, right.
Uh,
We've now
yeah.
come back to the data set conversation. So how did you create the data set?
Yeah, so this is actually also one of the main parts of the paper, right? Because in theory, this sounds like kind of difficult, because if you needed a list of annotated posts and someone writing descriptions, this would take lots of time and lots of resources that we don't have, right? So you kind of have to find the hacky way around this. And what we ended up doing was, so I already mentioned we had Kitty 360 list of instances and semantic meaning, and we also have a color channel available, right? Because they align images and LiDAR points. So what we ended up doing was we sampled a bunch of points all around cities, and then we looked at what instances are in a spatial neighborhood, right? For this, you really need 3D data, right? And then if you know that there is a house in front of you, then you can kind of generate based on some language template a description that mention these objects, right? And you can also mention something about color, for example, of the object that is in front of you based on extracted RGB color from instances, or semantic class, right? You also have semantic classes.
So in a sense, it's kind of synthetically generated data set. You pick a point and then you can come up with a list of possible descriptions that refer to that point.
Exactly, yeah.
Oh, nice. Nice. Is the model kind of end to end train from natural language to the list of predicted locations, or are you kind of tokenizing the natural language and trying to identify the landmarks as an intermediate step?
Yeah, so model is actually trained end to end. I mean, okay, sure, the coarse and the fine retrieval steps are trained independently, but other than that, end to end. So we have, we have point cloud encoders, and the language encoders.
Are the language or point cloud encoders are you using any off the shelf other models for those tasks?
Cannot think of any right now. I mean, our encoders are fairly simple. So for the text, we are actually just using LSTMs, not really any of strong state of the art encoders. And for uh, for point clouds, we use PointNet.
You talked about the data set that you created to train the model. That suggests that maybe you didn't have any external benchmarks to compare your performance to. But maybe you're publishing this and hoping to get other folks kind of using the same data set to create kind of compete for best performance. Is that kind of the thinking?
hmm Yeah, this is exactly what we did, right? So when we started investigating this, there was not no really data set or prior work to compare with. So this is kind of a first investigation into this into this topic. Yeah.
And do you think your initial approach did pretty well, and you nailed it, and there's not a lot of room for folks to one up you, or is it kind of a rough start, and there's lots more room to go to do better on the data set?
Yeah, I would say that absolutely the latter. I think that yeah,
I guess that's the humility test, right?
Yeah, well, I actually see it more that this investigation more that it actually opens more questions than answers almost. I mean, in the sense that earlier we just talked about this coarse localization step, right? For example, here this was one of the outcomes, that this is really the bottleneck, right? If you can coarsely localize yourself correctly, then you become pretty accurate at localization, but this is definitely right now the bottleneck, and I think that will be the first thing that people will have to look into how to improve. But of course, the question is now, I mean, of course, I'm sure that people can come up with better networks, right? And given data that we have, can localize, can improve localization scores, right? But there's also here just there's also just so far you can go, because there's this inherent uncertainty, right? Based on one description and not like very precise information, you could be in any of locations if you have big area to cover, right? So I think it will be really important to, as we talked about earlier, right, to align this with OpenStreetMaps and rely on more discriminative and unique cues for describing location.
Second paper that you are presenting at CVPR is focused on forecasting from LiDAR via future object detection, or at least that's the title of the paper. And the focus is kind of on joint detection and trajectory prediction. Talk a little bit about the motivation for that one.
Sure. Motivation here comes directly from robot navigation, right? So I was talking already earlier about object detection and object tracking, right? So object tracking is all about understanding how object moved in the past, right? But if you really want to navigate, it's not important to know where objects were. You have to know where objects will be, right? And one way you can tackle this, and this was already tackled in the community, is that you're detecting objects, you are associating them over time to get tracks, and then based on past tracks, you can like train some possibly autoregressive model that gives you prediction where object will be, right? But there are a bunch of problems associated with that, and one of them is that object tracking is very difficult by itself, right? And the question is even, do you really need um, do you really need object tracks to do forecasting, or could you just encode a sequence of point cloud and just train network to directly detect objects and predict where they will be, right? I mean, I'm not saying that tracking is not important. I think it is, but it might be that model actually implicitly learns by itself what it has to know about past positions of objects, so tracking kind of becomes implicit in this case.
In a sense, it's a similar bottoms up versus top down type
Mm.
of distinction that we were talking about earlier. The current approaches are kind of top down in that they're trying to identify object instances and then they have to track them, and they might be occluded for periods of time and things like that. And it gets really hard. And your hope is that, hey, just feed it a bunch of point data and let the network figure it out.
It's I feel that this is kind of a lesson learned over and over, right? Just fit enough data and let the network figure out things by itself. Don't mess with that too much. And I mean, I also have to say that by this, I'm not saying that tracking is not important, right? Tracking is important for a number of other applications, but when it comes to navigation, it really might be that what we need to look into is forecasting and not necessarily so much tracking. Although on the other hand, it's still nice to have this interpretability aspect of this, right? To that you get with tracking.
hmm and this is maybe jumping way ahead, but maybe there's some kind of multitask objective where you're trying to do forecasting but have tracking be kind of a byproduct of the network that um, has some of the benefits that multitask learning can provide.
Yeah, this makes perfect sense, especially if this hypothesis that I mentioned earlier, that if you know how to do forecasting, you somewhat have to know some idea about tracking implicitly, right? If this hypothesis is correct, then features that we learn to do forecasting should also benefit tracking, right? So I don't have answer for this yet, whether this is so, but I think this is definitely something that we should peek into.
So talk a little bit about your method.
Mhm. Yeah, so first thing I should say is that our method is not the first one that tackles end-to-end detection and forecasting. There have been very interesting paper on this topic before, for example, from a group of Raquel Urtasun from University of Toronto. And one thing that is quite unique with our method is that it actually offers multi-future interpretation, right? Forecasting is not something that I mean, forecasting is, as just as in the paper that we were talking about earlier, right? Is inherently ambiguous, right? Based on path velocity, you could make several guesses where objects will be, right, and our method is actually capable of that. And the way that we achieve this is actually in the end really simple. We just repurpose object detectors for not just detecting objects in the current frame that we just observed, but also in the future frames that we haven't observed yet. Um, so by encoding temporal sequence, you can just feed this sequence to the network and then say, hey, detect objects in current frame, but also in future time steps, right? So you will have multiple detection heads for future time steps, and you have supervision for that readily available, right? But what is nice with this is that you can then go, instead of like doing forecasting from time t into the future, you can do something different, and you can go into the future and backcast, right? So from the last detection, you can backcast the vector to previous frame, and from there to previous frame, and so forth. And then you will also have um, one-to-many mapping, right? So it might be that to one detection from t to t minus one, two detections might connect to this one, right? In this sense, you have one-to-many mapping, and this kind of defines this tree of possible splitting paths. And if you can connect your backcasts all the way back to particular detection, then you can say these paths are my forecasts, right?
Maybe I'm reading too much into this, but does this kind of open up some of the graphical types of tools to you?
Actually, we didn't use these tools, but this is one thing that we were definitely thinking next. That this is also something that we could do even more rigorously by relying on the graph neural networks, right? What we did was actually something rather simple. So we just have multiple network heads that detect objects in future frames, and then we just from each detection regress a single offset vector backwards, and then just based on Euclidean distance. Say whether some detection based on back asset vector connects with some detection from the previous frame. So in the end, based on Euclidean distance of the regressed offset vector.
For what did you use for data set here? I'm assuming based on the description that you needed to have labeled objects in the frames.
Yeah, that's exactly correct. So we used a new scenes dataset. So this is one of the popular automotive datasets that we are using nowadays. And yeah, for this we of course need supervision in the form of 3D bounding boxes and object tracks, right? Um, so we built on that.
So in the case of forecasting from LiDAR and the object detection, you mentioned earlier that this is a problem that has been well studied, and there are existing methods that have been developed to solve this problem. How did your method perform relative to the existing work?
Mhm. Um, well, I have short and long answer. So the short answer is it works better. Uh,
Okay.
the long answer is, and this was also a really big part of this paper, that metrics used in the past for this problem, for end-to-end detection and forecasting, were actually not the right metrics for studying this problem. And we actually have a big part of the paper showing this, that these metrics can be trivially fooled. And we also have proposed new metrics that don't have those issues. So I'm not sure into how much details you want me to go into this, because this is something that I could actually talk a lot about. But
I'm curious. I'd like to hear a little bit more. I mean, it sounds like
hmm,
if the metrics can be trivial, the old metrics can be trivially fooled,
hmm.
then your method performs better on both the old metrics and the new metrics. If nothing else, you could trivially fool the old metrics.
Yeah. So this is correct. Our method work well on both metrics, both sets of metrics. But yeah, the reason why we were looking into evaluation here is so previous metrics were adopted from more traditional forecasting setting that we're studying in the past years. And the other setting was that someone gives you ground truth trajectories, and based on given perfect ground truth trajectories, just predict continuation, right? But this is not the case in end-to-end forecasting, right? Because you don't have previous trajectories. Yeah, yeah. So in this setting where you have past trajectories, they used metrics that are called uh, um, average and absolute displacement errors, right? So absolute displacement error is quite simply looking at you look at your prediction, you look at the ground truth prediction, and if they're close enough, then you did a good forecast, right? But the farther away you are from the ground truth, the more you are penalized, right? And another metric that is usually used penalizes false forecasts, so forecasts that are nowhere close to any ground truth forecast. And one thing that community did when they started looking into end-to-end forecasting was that they evaluated separately object detection, and then they evaluated this absolute and average trajectory errors with respect to certain detection recall, right? For example, for 60 or 90% recall, right? And what can then in theory happens is that you train object detector in a way the detector will focus on detecting objects for which forecasting is easy. And there is particular type of forecast for that. And this namely are objects that don't move at all, right? That are just static there. And what is even more problematic is most objects don't move, right? If you're driving through the city, you see parked cars everywhere, right? And we actually have shown that it's possible to trick these metrics by a very simple baseline. And this is
Just
so-called
say that no object moves.
exactly.
Yeah.
Exactly. So we showed that this was the best approach, right? Better than anything proposed in the literature, which is of course not the case, right? Those methods are great. It's just that the metric was wrong. I mean, not wrong, but you could
Inappropriate
trick
for
it.
the data set or for real
Yeah.
world.
Yeah,
Yeah.
yeah, yeah, exactly. So our intuition was that we should somehow find a way to like not evaluation of detection and forecasting together, right? And intuitively, if you look at the object detection community, they really have great evaluation tools, right? Mean average precision is great metric that its values has survived the test of time, right? So our intuition was that we should use in one way or another MAP, mean average precision, and it turned out that this we can do this quite easily. Everything that we need to do is we need to change the matching criterion, right? What is considered to be true positive, false positive, and false negative, right? And what we said was, if you correctly detected an object and correctly forecasted, right? And these two, so that you both have correct detection and correct forecast, then you have a true positive. So this metric we call forecasting mean average precision.
So wanted to make sure we cover the third paper as well. You are a busy guy at CVPR. That one is opening up open world tracking. Yeah, tell us about that paper. What's the motivation there?
Yeah, gladly. So this is actually a really paper that I'm extremely excited about because the motivation dates way back in days when I was still doing my PhD, right? And I already touched earlier this problem of that we need to be able to track any object, right? We can't expect that we have training data for everything. And during my PhD, I was working on trackers for tracking any object, but here you really have fundamental problem, right? You would come up with a model and then you have to say how good your model is, right? But how you're going to do that, right? Back then, a few years back, we didn't have data sets or benchmarks or even the right metrics to talk about this. So I always had to find some hacky ways to make a point that what we are proposing works, right? But there was never like really a right rigorous way or benchmark that would really help community to rigorously evaluate methods, study progress, compare different methods apple to apple. So this the motivation for this paper is really to come up with tools to do this, so that community can make progress. And this is what this paper largely is about. So this paper doesn't really propose a drastically new method for this. It more than that, it rather proposes a test bed for evaluating this, and kind of we have experimental evaluation that consolidates different contributions in tracking by distilling out a good tracker, a good simple baseline for this task.
The tracker, is it a metric or a tool, an environment?
We actually provide a benchmark for this, and this benchmark consists of a data set, evaluation metric, and baselines, right? But the data itself, it's not something that we recorded. For data set itself, we repurposed tau data set. It's called tracking any object data set, and it comes from our collaborators. Back then we were collaborators when we started this. I wasn't at Carnegie Mellon yet. So this comes from the group of Deva Ramanan, whom I'm also now working with. But Tau dataset by itself was released to study tracking in the long tail, right? But not in the open world. And with this paper, we repurposed it for studying object tracking in the open world. And what we did was um, we split training and test data as follows. We For training the models, we proposed to use Coco dataset that has labels for 80 object classes, right? And then in Tau dataset, we have labels for several more objects, right? For hundreds of object classes. And we then define a test bed such that you train your models with knowledge of 80 classes, then you do validation on additional set of semantic classes, right? Then you have additional test set in which you have semantic classes that don't even appear on validation set, right? So that you make sure that nothing is, kind of leaking from one split or of another. And here's actually one important distinction, because usually you make sure that when you have training, test, and validation split, that the data doesn't overlap, right? And you also have to make sure that that semantic classes don't overlap, right? So that in each set you have semantic classes that you can say, okay, these are the unknowns, and I didn't train anything or tune any parameters with knowledge of these classes.
Got it. Got it. Got it. So when you say open world here, are you using that term colloquially, or does that have a specific meaning, or does it refer to a specific environment in this context?
So the term itself, open world, is of course borrowed from the community, right? You probably know about this classic work from um, Bolt and Bendale, right, where they studied open world recognition, and there they study open world recognition in the sense that you have some certain closed set of object classes on which you train your model, and then during the deployment phase you will see new objects you haven't seen before. You have to recognize them, then you kind of have to ask annotators to label them, right? So we borrowed part of this idea behind this, right? So we also have some closed world data set, right, in which we have some finite set of classes labeled, and then we study performance of those models in an open setting, in which classes that we haven't seen during training also
Got
appear,
it.
right?
Got it. So
But
it's describing the setting. I think I was
mm,
envisioning like a simulation environment that was a
uh,
world that an agent would explore, kind of thing, but
mm.
that's not really what we're talking about here. Did you also, so you provide this data set and this kind of benchmarking approach? Did you also provide kind of proof of concept models? Did you kind of bootstrap the effort, and what does that look like?
Yeah, so This I would say that it's something that is rather simple and builds on really on contributions from multi-object tracking community. So the tracker itself is at the end of the day really follows this tracking by detection paradigm, right? Which means that you have some kind of object detector that gives you possible object detections in each frame, and then by some means you connect these detections over time, right? But there are, of course, certain important differences. And first one is that your that you cannot really, train object detector for object class for which you have no labels for, right? So this object detector is a bit more like object proposal generator. I touched this briefly at the very beginning. So we just repurposed MaskR CNN. So in particular, the region proposal mechanism of MaskR CNN, but we also made sure that we obtain object instance segmentations for each proposals, right? And these proposals are then kind of you have lots of them in the image, and they are like kind of input to the tracker, and then tracker figures out over time which proposals are temporally stable, right? Which it can connect over time, and those will be then our object tracks.
When you describe the simple method of kind of this proof of concept method that you ran against the benchmark that you're proposing, it sounded like what we described as kind of this top down traditional approach where you have these objects and you're trying to track them across time, the objects from bounding boxes that you're trying to track across time. When we previously spoke about the forecasting from LiDAR paper, we kind of contrasted that top-down approach with the bottoms-up approach that starts at point cloud, or in another setting maybe pixels. And I'm kind of wondering if the methods that you developed in that paper could be a future direction for someone tackling this open world tracking problem, or are they, I'm really trying to test my understanding and see how they fit together, or are they totally unrelated and I'm off here?
No, so it's not totally unrelated. So there are some gaps definitely, because what I was talking about at the beginning, it was mainly 3D computer vision, and it was largely relying on 3D sensors, right? And this opening up open world tracking is purely image based. So here we haven't talked about 3D at all. But there is one thing that if I understood correctly, that you were asking if we could, instead of doing this separation, detection and then linking things, to do something more like we did in the previous two papers and just do everything in end-to-end manner, right? Um, and indeed, the community is definitely moving in direction of doing multi-object tracking in end-to-end manner. And there are several very nice approaches out there to do that. Methods that based on graph neural networks, or just regress targets, or use end-to-end transformer based detectors for tracking segmentation. So there are many of them, um, but this particular dataset and challenge makes things especially difficult. Because most tracking data sets before focused on tracking pedestrians or cars and pedestrians, right? And you will have a few objects in the scene and shorter sequences. And this data set is really huge, and you have jungle of objects pretty much, right? And we just haven't been able to apply those methods to this problem yet. You very quickly run into issue with memory and training time and so forth. So I think that the method that is closest to being end to end is Tractor, that also comes from Laura's group, but Tractor um, was lagging behind the baseline that we proposed.
Well, Alyosha, it's been really wonderful learning a bit about your research and CVPR papers. We'll, of course, have links to the papers on the show notes page for folks to check out the full details. But wanted to thank you for taking the time to join us and share a bit about what you've been up to.
Yeah, I would also like to thank you for inviting me here. I really had a great time discussing our recent research. So it was a really nice discussion, and yeah, um, I hope to see you at CVPR as well, and I'll also encourage the audience to come to our posters, or just if you see me anywhere, just wave, and I'm always happy to chat about research anywhere, anytime.
Awesome. Thanks so much.
Thank you. Bye bye.